In today's class we are going to study capacitance for parallel plate capacitor with dielectric slab, and with this we are going to study for spherical capacitor as well, okay, which is not in your NCERT text but it's in your both. So let us consider. So here you can see in the diagram, here in the right hand side there is a capacitor with two plates, one positive and one negative, and which are d distance apart, you can see in the diagram, and there is one dielectric is kept, insulating material is kept of thickness T. So okay, T is the thickness of, and let's say the external electric field applied across the capacitor across the plate is E, developed, not developed, you can say it's. So here are two plates, distance between them is d, area of each plate is A, and dielectric slab of thickness T such that D is less than D, means is kept in between two plates. So it is clear that the length D and T part is filled with so only the T part, it's partially filled, it is not completely packed by the dielectric slab, and whose permittivity is epsilon, and the dielectric medium is having a permittivity is epsilon r, and it's okay, this is quite clear. Now plus q charge is given on plate, on the plus q charge on the plus plate, as a result of which electroinduction minus q charge is developed, induced on another plate. Okay, the surface charge density on the plate is sigma is equal to q upon A. We simply take electric field intensity between the plate at any point in air is E1 is sigma upon epsilon 0, which we already said when there is no dielectric. Okay, let's say that there is no dielectric present between them. So in that case, the electric field between the intensity between plate is sigma upon epsilon 0, or sigma is simply surface charge is q upon A, so it is q upon A epsilon 0. It is not there. It is there, you can see in the below. E0 is when there is no dielectric. Here you can see sigma upon 0, and sigma, as we know, q upon A. Q upon A, it is wrongly written. Okay, so it is q upon A epsilon 0. It is q upon it is not q into A. Now when the dielectric is placed of thickness T, which is, see, so there is some area left, or there is some space between the plates and the dielectric. So there are two, so that means there are two mediums. One is air, then dielectric, then air. So total overall the thickness of slab is T, and the thickness of that air, or you can say air column, is simply T minus D minus T, as D is the total distance between the plates. So there are two mediums together. So T is the thickness of that slab, and air which is present, okay, it's a thickness we are talking, we are taking a column, so the thickness of that both the columns together is D minus T. And again the electric field in between, as we know, the dielectric place, the electric field between the plate is simply what, sigma upon epsilon 0 into epsilon r, as there are two mediums, or simply after putting sigma it's become okay. So potential difference between the two plates is, so we have to consider both this space where air is present or vacuum, or the dielectric together. So the electric field due to, so the potential we know the, so you can now see here in the left hand side, V is potential difference between the two plates, which is simply equal to E0 D minus 2. As we know the potential difference formula, from the potential difference formula, what is that? E0 is simply E into D, where D is the separation. So here when we take air separation, so air the part of air in this is simply D minus T. So E0 into D minus T due to air. Okay, electric potential due to, and the second term En into T. So here the N is for the medium, the electric field generated due to dielectric, and T is the thickness of that medium, so it is En into T. So instead of En, and so what, as we know, K is equal to E0 upon the dielectric constant. K is E0 upon E, or simply En, you can say it's En, or simply En is equal to E0 upon K. So that En value we can substitute up in place of En, so we'll got this solution. V is equal to E0 D minus T plus E0 upon K into T. Why we have done it? So that we can take out common, we can take out E0 common. So after taking out E, we got only D minus T plus 1 upon K. This is potential, and after getting potential we can simply find using the capacitance formula. Capacitance is simply C is equal to Q upon V. So in Q upon V, so V, after substituting value, the capacitance due to partial, okay, plate, parallel plate when filled with partial dielectric is simply, so there are two, the one when it is completely with dielectric, so you only one term is responsible, which is En into T, En only, En into distance. But because as there are two mediums, so the result will be little different. If the dielectrics have occupied the whole space between the plate, then T and D is become equal, so the formula will be reduced to the earlier formula. Now we have to okay, before we go to Van de Graaff generator, there are some other dielectrics also, so which is not here, so I'll will go to our book part. Okay, here it is. The problem, it is in NCERT textbook, it is in the problem. A spherical capacitor, okay, we have not learned. A spherical capacitor consists of two concentric spherical conductor held in position by suitable insulating support. Show that the capacitance of a spherical capacitor is given by. So we have a, so it is simply that capacitor. We are, what you can see in the diagram, the capacitance is given by this. So what we have to first see, R1, okay, this spherical capacitor, concentric spherical conductor. So there are two spares concentrated in the same center. So one of R2 radius, the smaller one is of R2 radius, and the bigger spare is of R1 radius. Okay, it is written where R1 and R2 are radii of outer and inner spare. R1 for outer and R2 is for inner. So let's do how to get the value. We have to go for our board. It is in your now derivation. It is in now both textbook. Okay. As the tools, one radius, first radius, inner and outer radius is R1 and inner radius is R2. Let me start. Okay, the first step is to find the potential. How to start? Let's say consider a spherical capacitor. It consists of two concentric metal sphere. Okay, so I'll make a diagram first of all. Yeah, take a sphere. Okay, I made first smaller sphere. It's not a sphere, but Okay, then I choose another color to lighten one. Then I'll choose, no, sorry, I have to choose a bigger one. Squat. Okay, sorry, my mistake. What I will do, I'll choose a first bigger spare. It's much easier. And what happened now? Okay, and from this side I'll choose a darker one. So my mistake should be spare. Oh, this I am getting little difficulty in drawing inside. It is not like that. There are two spares. The inner from the center. So the radius of inner one, outer one is R1 as we have seen, and our inner one is R2 if you remember. And let's say now this is charge. It is very easy how to do it. We simply what we do by and in actual diagram how this actually built. So this inner spare. So let's say this inner spare, I'll choose a color. So red for best thing. So the inner one, somehow this inner cylinder is positively charged. Okay, the adjustment is there. Let's say it. And as a result of which due to induction the inner layer of the second spare in the inner layer the negative charge, so the negative charge develop. So the positive are outside and so positive and negative. You can see inner one is 40 charge, so because of this induced charges develop inside and outside also. If I'll try to draw, positive charge developed, but somehow this charge is simply by using a, I'd say by earthing the outer layer, earthing. Okay, I'll earth it. So this all positive charge goes down, so there will no positive charge. Okay, the positive charge developed in the outer layer are all distributed all over the place, all around the sphere. But okay, and as soon as we have grounded the outer layer, so this is how the capacitor is made. Okay, let's read it. Suppose the radius of, yeah, I think it is clear how the spherical capacitor is made. The inner sphere is somehow given some positive charge, and due to this the inner layer, okay, the inner layer of the second sphere, so the larger sphere got negative charge induced, and so the outer layer of outer sphere become positive, and which on grounding it become all the new positive charge goes. Let's say when plus charge is given on the surface of inner sphere, okay, then due to electrostatic induction on the inner face of sphere B, so the let's write it actually. No, what I do, yeah, I cancel, I choose blacky pen. So this is A and this is B sphere. Okay, that's what I'm reading. So what I'm reading, just read it. Suppose the radius of sphere A is R2 and the sphere of radius is R1 inner radius. Or vice versa, whatever. You can see the sphere of radius A is R2 and sphere of radius of sphere B is R1. So between the plate, a dielectric medium is placed having the dielectric constant epsilon. When the charge plus q is given on the sphere A, then the two electrostatic interaction on the inner surface of sphere B, negative charge developed induced, where on the outer face plus q charge is developed. Due to charge neutrality, the negative charge present on the inside face of the sphere B remain bound to positive charge. Okay, as we have done this process already. So now the potential at point P situated on the surface of sphere A. Okay, on the sphere A at point P, wherever it is, you can take any point. Okay, not important. On sphere, on the surface of sphere A, the potential due to plus q charge on the surface is simply due to charge surface sphere A plus potential due to. So there the total potential on sphere A is due to, is simply written as VA. I'll write it VA is simply Q, or I'll rub it just for more simplicity. Sigma, the potential due to sphere. So which simply says Q upon 4 pi epsilon 0 and epsilon R2. Okay, plus one more term, because around the plus charge there are also negative charge, you can see in the inner part. So it is due to minus q 4 pi epsilon 0 epsilon r1. Okay, why the epsilon 0? Okay, but there are two terms, but both having different radius, so that means you cannot cancel it. On the surface the distance is r2, and on inner surface of B the distance is r1. So that is why the potential difference is this much. So after solving this, how much I got? So let's rub it. So you can take out q 4 pi epsilon 0 outside. So what is left? So I will also do. So what I left with, and this minus sign, I'll just here put it here. So this become minus. So the result will simply be, I'll take a bracket here, 1 upon r2 minus 1 upon r1. I think it is clear. Okay, we are taking common for q upon 4 pi epsilon 0 r2 upon r1, or by simply taking the LCM, I am keeping other constants there, so it becomes simple r1 minus r2 upon r1 into r2. Okay, that is much, and remaining things are here, the things are here, this whole thing is still here. Now what I need to do now, as if we talk about the potential of outer layer of B, so this is the total potential, member. Since sphere B is outer layer of sphere B is connected to earth, so the potential of B simply is BB is 0. So what I'll do, I'll rub this part downward or upward. So I'll just write out, you just remember what I have done. Very small rubber, but we have to do it as our board is also small. So the total will be BA minus BB, and BA comes around q upon 4 pi epsilon 0 epsilon r. Okay, I'll make it more clear. epsilon 0 epsilon r r1 minus r2 upon r2 r1. Okay, that is there, you can see. So after we know, as we have a process, we after we got Va minus Vb or potential difference, we simply go for capacitance, which simply says Q upon what? Q upon Va minus Vb potential difference. So substituting the value, the Q will cancel out. 4 pi epsilon 0 goes up as it is in the bottom, Va minus Vb. So the answer will simply be, if I'll rub further, so our answer, I'll draw the I shift, okay, I'll remove the diagram. So I'll do, so putting the value, so what will be our answers after solving or putting the value Va minus Vb over here? So r1 r2 will goes up, r1 minus r2, and 4 pi epsilon 0 epsilon r also. So our answer to that will be 4 pi epsilon 0 r1 r2 upon r1 minus r2 for spiral. So remember one major common thing. Again, you have to go back and start chapter 2. We'll go to the bottom. What was our problem? There is a problem. Let's see. Here. So problem was to find. So this is the answer which we have just derived. The spherical consists two concentric spherical conductor. So in this, there are only two steps. Okay. Whenever the problem comes to find out the capacitance of any type of capacitor, the first step of your, if I go for the new one, the first step is to start with potential. First is you have to find potential either, okay, that means V, and after you solve the value of, you got the value of V, second step to substitute the value in this Q upon V, and you got solution. So there are only two single steps for every type of capacitor, whether it's parallel capacitor or anything else. So there are, we have used epsilon 0 and epsilon r because there is a dielectric medium between these two concentric sphere. Okay, so it is not vacuum only. If there was vacuum, we would have taken only epsilon 0. There are alternative method also to do that, so you can check it out. So now after finishing this, there are few, I'll go for the new. Now let us capacitance of cylindrical capacitor. What? Cylindrical. So how to draw cylindrical? This. Okay, we have to draw the cylinder. But cylindrical capacitor also having two cylinders. So one is inner one also. Just like two spare. Okay, let's say the inner radius again. Either you take inner one radius, let's say A, and the outer radius you can see B, and as it is very clear that B is greater than A. The radius of inner cylinder is small a, and radius of outer cylinder is B, and B is, as it is very much aware. So here also somehow a positive charge Q, if I'll choose red one, somehow a positive charge is given to cylindrical surface in a outer surface of cylinder A. This is A cylinder, and inner cylinder is A and outer cylinder B. So due to induction, negative charge will develop. I'll simply choose a green one. Sorry, my mistake. I have to choose green. So negative charge will develop in the inner layer of sphere B, and the positive charge also, which can simply be removed using by grounding the outer layer, which as we have done in sphere. So after this we have to find electrical potential between the, so our aim is to find the potential between plate A and B. So to find out the electrical potential for plate A and B, we will use an alternative method, so that you are familiar with the other one, which we, the method which we have used in for a spherical capacitor is a classical method where we, okay, now as we have learned integration and differentiation, so here we will use integration or method, or simply I mean using Gauss theorem. So how to do it? Let's go start a new one. The first is to find out flux. From flux definition, it is simply E ds, as due to inside one. Okay, then the capacitor sorry, the cylinder A, which is inside one, and we have done for cylindrical the electrical field, so we have discovered, and this equal to Q upon epsilon 0 by Gauss. So an EDS value, to find out the EDS value for cylinder, if you remember, if you can check out from left for cylinder, E is only for surface area and DS is the surface area here, because both the top and bottom have no contribution to flux, so it will simply E 2 pi RL is equal to Q upon epsilon 0. Okay, E is the electrical field, and so by solving this you can simply find the value of E, which is simply Q upon 2 pi RL epsilon 0. Q upon 2 pi simply E is equal to Q upon 2 pi RL epsilon 0. This is the value of E. Now after getting here in this integration method, this is the technique we use, and once we got E values, we can find out the value of V, because there is a relation between E and V. Remember? So the putting, so what happened now? How to check out? Yeah. So VA minus VB is line integral, na? That we have done. This is the theorem which we have done. E dot the line integral, or is we can take simply E. What is DL here? Remember the distance between the radius difference between the two cylinders. So let's say the distance is dr. Let's say distance dr. So I can simply dl come into dr. And after substituting a value b to a, e value we already have measured, to epsilon 2 pi epsilon 0 l, no, epsilon 0 r, sorry, r l d r. So after taking, I'll start. Let me start again. As we have known that VA minus VB is equal to minus A, sorry, again it came A to B E dot dr in this case, because dr is the distance between two. Let's say r and 1 plus r. So now after substituting the values, we got minus A to B, once oh. So E value we already have measured, so Q upon 4, no, 2 pi R L, let me write again, epsilon 0 into dr. How to solve it? As there are no remaining terms except r, so it is a integration with respect to r. So what we'll do, we take out all the remaining terms outside. So what is left between here? There are terms, I'm just leaving outside terms. So 1 upon r dr. And how to solve it, and the solution of this, if you check out the integration for r minus 1 dr, okay, so it is minus plus 1 0, so 1 upon r is simply, if you check out, so the integration of 1 upon r dr is simply log r. I'll go to the another slide. So it's simply equal to q upon minus 4 pi, no, sorry, it is 2 pi L epsilon, which is taken out, and the value that come around log r A to B. And when you solve this will be a minus, okay, B, I am just simply writing B. So log, first I will put log A and log B. So after putting this will come around log A minus log B, and minus sign, as the minus sign is outside, this minus sign, we take this minus sign inside, so this become minus and this become plus. So it can be written as log B minus log A, and log B minus log A, if you remember, it can further be written as log B, sorry, log B upon A. So answer will be simply q upon 2 pi epsilon 2 pi L epsilon 0 log B upon. The actual I'll go to the next slide, new one. So it will be simply q upon 2 epsilon 0 L, okay, I'll just write it epsilon L log B by A, which is V. Now C is obviously q upon B. Substituting this value, this q will cancel out and other things will go up and down, this we know. So what will come up to 2 pi epsilon 0 L will goes up and log B upon A comes down. So this is for cylindrical. Okay, so two derivations we have done. For first we started, if I'll revise, so the first one was for parallel capacitor having a dielectric rate of thickness T and the distance between the plates is T. So again here also we have done. And the second was spherical capacitor with two slabs. The third one was two cylindrical. If all around we check the value of capacitance. So for that, this we have found C for this and C for this. So out of these three, any one can come. I'm definite because every year one will come to find out the capacitance. So we have learned the olden ways. We have learned using the Gauss theorem also how to use this, because when you find the electrical field you can simply go for cap and then for potential, and then so the simple. Okay, uses of capacitor. If we look at the uses of capacitor to produce electric field of desired pattern, so let's go to our, if it opens, again having problem. So I'll go to my slide best way. Let's see whether it is working or not. It will again load, and that because you can open every slide, you cannot not maybe here. So let's see. So the energy stored capacity. So in this, out of these, how many, what we have done is electrical capacitance, principle of capacitance, capacitance parallel, another three also. Polarization vector, dielectric strength, parallel plate capacitor with dielectric slab. Okay, there is one more important small 2-mark questions which is not in your NCERT textbook. So we have to, and one more question, bigger question. The relation between, remember, the relation between electrical susceptibility. Okay, let's go it. I think I should go it for a shorter time, because tomorrow we will do very good questions. The relation between electrical susceptibility XI, this is called XI, and epsilon r. Or what is the relation between the two? XI is called electrical susceptibility. Yes, electrical susceptibility, and epsilon r you already know, relative dielectric or relative permeability. This is very important derivation which usually they ask in exam. So what is it? It is very easy to understand. We have learned how when a dielectric is placed in electric field, how they got polarized, and to measure the polarization. When a dielectric, in dielectric, when you have placed this dielectric medium, you already done it, remember, in earlier class. So what say we have a new polarization vectors polarization vector P, and it's simply n times P. What I am saying, P is a dipole moment into n is the number of molecules per unit volumes. So how much any dielectric is polarized are all the it means polarization means all the molecules per unit volumes are polarized. If there are n molecules per unit volume and each molecules having a dipole moment P, so the total polarization measured by P vector, which is simply n into P, and that polarization depend also, and that polarization P how much is depend upon. So there is a relation which says the polarization is directly proportional to electric field. So once you remove that sign, P is equal to the proportionality sign, then we simply put xi epsilon 0 into E. Okay, they both become constant. Or you from this you can simply I'll go to the next slide. Okay, next. So xi you can simply find out xi is equal to P upon epsilon 0 into E. And as we have known that if E is the electrical field of this due to outside, okay, parallel plus and this minus, and as you have placed the dielectric, it also electrical field which is in reverse direction, let's say this is EP. So the total because they so the total electric field is simply E0 minus EP. Okay, E0 minus EP. Or on a further note, if we will go, then E is equal to E is equal to E0 minus, again it will come, take EP, to we'll got E0 is equal to E0 plus EP. So E0 plus P upon, where EP is polarization, so epsilon 0. And as we have found the value of P, okay, this P is polarization vector, so we'll further get value of, don't say, after substituting we'll got E0 is equal to epsilon 0 E upon, so cancel out, so we got this. So what we'll do, we can take out, it is E, okay, so xi E only left, so it is only xi E. So E can be taken out, so it is simply 1 upon xi. So E0 is equal to E1 plus xi. On further, so we'll take E on the other side, so it is left with 1 plus psi. This is term is epsilon r, relative permittivity, 1 plus psi. So this relative permittivity and psi, there is a relation. So this is for now, and tomorrow we will study about what? Well, what I told is very important topic. Just see it how this work, Venn graph. generate. And the graph chart. That's for now.